We have this function f of xy that forms a three-dimensional shape over the box outlined by x between -1 and 3 and y between -1 and 3, and we are going to analyze it in a few different ways. The first step is to visualize the two-dimensional rectangle that the shape falls within, and luckily we see that it is just a square, which makes things pretty simple. So next we are going to find the volume of the shape above this rectangle. To find the volume of a normal shape, we typically multiply length times width times height. And we see that the length and width are defined by the square, but the height is described by the function f of xy, so it's not a constant height. So instead we will use a double integral to find the area under the curve of f of xy bounded by these x and y regions. As you can see, we evaluate the integral with respect to y first, then with respect to x, and we get a value of 16. This means that over top of this box that we've drawn in between f of xy, there's a volume of 16 cubic units. So next we want to find the average value of f of xy. So to do this, we just have to divide the total volume by the area of the square. And we see that the area of the square is a length and width of 4, so its area is 16. So we just have to divide the total volume by this area, which is just 16 over 16, which is 1. So the average value of f of xy on this domain is 1. So now we are going to find the absolute maximum and minimum values of f of xy in this domain. First, we will find the partial derivatives with respect to x and y. And now we want to find critical points. Critical points are just points where the function is not increasing or decreasing in any direction. So to find these, we are going to set f of x and fx and fy equal to 0, and then solve for x and y. When we do this, we find the critical points 1, 2, 3, 0, and 0, 0. But we know the absolute maximum and minimum values can also happen on endpoints along the edge of the domain. So now we have to check each side of the domain. First, we will look at L1, which has y equal to 3 and x between -1 and 3. We can write f of xy as a new function with y as a constant 3. Then we take the derivative of that new function and set it equal to 0. When we do this, we see that x equals 3 over 4. So a critical point on this line is 3 over 4, 3. We can continue the same process and see that on L2, there's a critical point of 3, 0. But when we do this, the same thing for L3 and L4, the critical points are not in the domain, so we can just ignore these. We also have to remember that the endpoints at the corners of the domain also have to be evaluated. So when we have all of these critical points and endpoints that are potential absolute maximum and minimum values, then we evaluate them all for f of xy, and we see that the maximum value is 27 at the point 3, 3, and a minimum value of -9 at -1, -1. So now we're just going to find the local minimum and maximum values as well as some saddle points. So we're going to use a second derivative test. We already found the first partial derivatives, so now we will find the second order partial derivatives. Then we want to plug these into this function for d as shown, and we will evaluate our 3 critical points that we found earlier in d. We don't have to do any of the endpoints because local minimums and maximums and saddle points can't be along edges. So we see that d evaluated at 1, 2 is positive, and fxx at 1, 2 is also positive, so there is a local minimum at this point. Then for both 3, 0 and 0, 0, we see that d is negative, which means that these are both saddle points. So when we plot this shape on our domain, we see this shape here on the left, and we see that there are in fact 2 saddle points and a local minimum at these values.